Oh man, I hope I do a good job for you guys. Okay, so you guys are supposed to learn some thermodynamics, solving problems with me. Okay, I'm Sean Kelly, and we'll get an introduction. So you guys, how many people have the book with them? Nobody. Okay, cool. That's great. No, what it means is that if I read it out loud, you're gonna quickly write it all down. I don't know. It might not work. I can tell you what the relevant information is, and from there, that's what we're going to work with to solve the problem. So, but I'd like you to be able to look at it. That would be easier, wouldn't it? A lot easier.
Dr. Young, you grew taller.
Dr. what?
You grew taller, Dr. Young.
Yes. Okay, so I'm taller here. I'm taller than Professor Young. No. Okay, so they call me Sean, but you can call me whatever you like. I'm technically a doctor. I have a PhD in physics, but I'm a little rusty, so I'm hoping I don't make any mistakes for you guys today. So if I do, actually it's really kind of important. If you see me make a mistake, you want to stop me right away, because I don't want to go down the wrong path. That happens, and I might make a mistake. I'm a little nervous. You know, you guys are really good students, so I want to do a good job for you. So,
how do you know we're good students?
Well, I'm assuming that you made it here this far, and you're going to go further, that you are motivated and interested in learning physics. So, and I've talked to some of you before, so that's how I know. Actually, I've just seen some good stuff here. We got it? What do you think?
These are all the illustrations from chapter 22. If you
awesome.
back
Okay.
up, you can go to the other chapters. So.
Oh, no, 22 is good, because that's what we're doing right now. Thank you. Okay, so I don't have the book, but I'll read the question, and then we'll get the relevant information. Sorry about that. I should have planned a little better. So you want to listen to what the problem is about. I'll be very good about writing down the important information for the problem. And that's kind of a key thing for problem solving, right? To write down what are you given in the problem, and then relate it to how it's important for solving the problem, actually. So let's see, we're going to start off with, there's no diagram. Okay, we're going to start off with an easy one, right? We'll start off easy. We're going to do a few problems today. Let me write down the list of problems that were given to me. And we can do more if we have more time. If we don't have enough time, then I did something wrong. But we can also go back to old homework assignments if you like. Again, I'm a little rusty, so give me a chance to catch up. I'm sure I'll be able to help you. Okay, so we're going to do today chapter 22. We're going to do problems, if everything is great, we're going to do problems 4, 14, 20, 36, 48, and 55. And you know that in the back of the book, if you had the book, they have the answers to the odd questions. Well, Professor Young gave me the list of questions. I did the problems, and then I didn't have any way to check them. So I was a little concerned that maybe I didn't have the right answers, but I actually was able to check a bunch of them. And now I have the solution manual. Whew. So before we say everything is said and done, we'll just check to make sure that the solution that I got is in fact the correct solution. Okay, so we'll start off with number 4. And again, you want to just listen to the relevant information. Okay, so we're going to set this up. It's a little bit of work. It's mainly a problem of keeping track of units and a bunch of numbers. There's a lot of numbers in here. Okay, so problem number 4 says a multi-cylinder gasoline engine in an airplane operating at 2,500 revolutions per minute takes an energy of 7.89 times 10 to the third joules and exhausts 4.58 times 10 to the third joule for each revolution of the crankshaft. How many liters of fuel does it consume in 1 hour of operation if the heat of combustion is 4.03 times 10 to the 7th joules per liter? What is the mechanical power output of the engine? Ignore friction and express the answer in horsepower. Okay. What is the torque exerted by the crankshaft on the load? And what power must the exhaust and cooling system transfer out of the engine? Okay, so I read the problem. You have the overview. Let me go through the problem and write down the important information. So number 4. They start off by telling you that this engine is operating at 2,500 revolutions per minute. Anybody tell me what that would be? Okay, so we're off to a grand start. Let's call that omega, right? The rate at which the cycle is taking place, right? That's called omega. Now, it's 2,500, and you're going to see this in engineering manuals. It'll say RPM, right? But in physics, we tend to try to write things so that it's easy to work with them. We're going to say revolutions per minute. Okay. Now, I want to remind you that that is not the way that we usually measure angular velocity. How do we typically measure the angular velocity? Radians per second. So I'll come back to that in a moment. It turns out this is going to be fine for a number of our calculations. In fact, for most of our calculations. But one of them we're going to need to change that to radians per second to get the easy answer. Okay, then it says, okay, here's an important part. It takes in energy. Now, what kind of energy are they referring to that you take in you're an engine? What kind of energy would that be? That's heat energy, okay? So the heat energy is coming in by the combustion process. We're going to call that QH, right? Because that's the heat energy that's coming into my engine from the hot side. It's feeding thermal energy into the engine. It's 4.58 times 10 to the third joules. Okay, so it takes in this much heat energy, and then at the same time, it says that it expels wait, I said this wrong. It takes in 7.89. I'm sorry. Wow, my first mistake. Okay, don't worry. I'll make plenty of them. Okay, here we go. 7.89. Oh, and then if it expels the energy, what would that be? That would be QC. Okay, to the cold side, it's expelling the energy, and now we're going to get our number 4.58. 4.58 times 10 to the third joule. That's each cycle, right? Each crank, each cycle, each revolution. Yeah, let's say that. Each revolution. Okay, each revolution, that's how much energy goes in and how much energy goes out. They tell you the heat of combustion. Okay, so I'm not sure how you guys have done heat of combustion. Have you done that before? Okay, have you done heat of vaporization? Have you done heat of fusion? So we've got this heat of combustion, that's all. It's another way to derive heat. What was the symbol that we used for latent heat of fusion or latent heat of vaporization? L, LF, LV. Why do we call it LC? Should we call it that? So latent heat of combustion, something like that. It's the amount of heat energy per, well, it'll tell us in a moment. It says that it is going to be 4.03 times 10 to the 7th. Wow. That's a lot, right? 10 to the 7th. That's 40 million joules per liter. Again, I'm not sure why the book focuses on liters. You guys know why? I don't know. In physics, do we do liters usually? What's our typical unit? Cubic meters. Now, it's going to come up a bunch today. So you should easily be able to jump from a liter to a cubic meter. Does everyone know how to convert from a liter to cubic meter? Divide by 1,000. Okay, cool. All right, so good. So one liter is 10 to the minus third meters cubed. I don't think we need it for this problem, but we'll definitely need it later in the lecture here. All right, so I think we can get started. Are we ready? Let's get started. Oh, it says in 1 hour. Okay, so in 1 hour, we're going to talk about what happens to this machine. That's my time. It's 1 hour. Okay, if you're ready, let's get started. So the number one question, how many liters of fuel are burned, or how many liters of fuel does it consume in 1 hour of operation? Okay, now that's a pretty easy question because which energy is the energy that's going to be used by the engine? Or, I'm sorry, which energy are we feeding into the engine? There, right there. Okay, in 1 hour, how much total energy will we need? So here we go. What is the total energy needed? How many liters of fuel will be required to derive that? So we are actually feeding QH. By doing this combustion, we're feeding it into the system. That's our QH. So the total amount of QH, if you look at this is actually the joules per revolution. I could even put that in there if you like. That's joules per revolution. Does that make sense? Because it's exactly one revolution that's taking place. So if you want to think about it like that, we have 7.89 times 10 to the third joules per revolution. We've got 2,500 revolutions per minute. That's great. And the last thing I need is what? I want joules, so I want to get rid of the minutes. I need to know how much time. 1 hour is 60 minutes. Okay, and thankfully it all works out. That's great. So in 1 hour, I will have used, I've done the calculation. You could check me, by the way. If you had a calculator and I talk slow enough, then you could just double check that I didn't screw up. Oh, I have the manual. Okay, I guess I could get the manual out too. We're planning ahead here. This is good. Planning ahead is good. Okay. Chapter, oh, isn't that funny? Oh, that is so, the last chapter in the book, 22. Awesome. Okay, great. 22:4. Oh, let's see if I got the right answer. Oh, I didn't quite get it yet. Okay, so we have the total amount of energy. I'm going to write down what I got, and then we'll check it in a second. I get 1.184 times 10 to the 9th. 10 to the 9th joules. I don't know if he talks to you a lot about significant figures. Yes? No? I'm going to throw it in there. In my calculation, I have 3 significant figures. So I want my answer to be 3 significant figures, but I don't want to screw up by rounding off too early. So I always keep 1 extra in the middle of the calculation. So I've got 4. So my final part, I want to know how many liters it takes to get this much energy. And the formula is something like this, M times L, right? That's something like the formula. However, it's joules per liter, so that's not quite right. In this case, I'm going to have to multiply by what? The volume in liters. So this is not quite the right way to do this one because the latent heat that they gave you is per liter. I'm going to really have to use 4.03 times 10 to the 7th joules per liter times the volume in liters, right? And that way the liters will cancel and I'll get joules again. But again, this is going to generate my QH, So how will I get the volume? Take my total energy divided by the combustion coefficient here, the combustion thing. All right, the energy of combustion. And I get a volume. So for part A, I'm finally going to have the volume, 1.184 times 10 to the 9th, divided by 4.03, 10 to the 7th joules per liter. Again, the units work out. That's great. And then I get 29.4 liters. Okay, and just to check, I mean, it seems like a reasonable amount of fuel, right? Not too much, not too little. If I got millions of liters, I'd kind of question that. And if I got 0.02 liters, I'd question that. That seems pretty reasonable. Okay, 1 down. B, we've got to talk about what is the mechanical power output of the engine. So we're talking about the power output. Where do you get your power? What's the formula for power? Okay, so for part B, I'm kind of trying to work this. I didn't leave myself enough room. Maybe I'll start over here next time. For part B, we want the power. It's the work that comes out of the engine divided by the time it took that work to come out. There you go, simple. So how do we get the work that came out of the engine? This is omega. This is W. They look a lot alike. So I'll try to make this straighter. How about that? W. Okay, work. How do you get the work that came out of the engine? Conservation of energy, right? So this, you put in this, only this much came out. Where'd the rest go? You got work. The work, conservation of energy, is the hot energy that went in minus the cold energy that went out, right? Conservation of energy. So that's pretty easy to calculate. And this is per revolution. Okay, so you could do this a couple of ways. What did I do? I did per revolution. No, I didn't. I did something arbitrary. I did per in 1 minute. Okay, just to make it easy. I don't know why that makes it easy. Do you? Otherwise, how much time would it be? You'd have to divide. This is going to be each revolution. How much time would it be if it's 2,500 revolutions per second. It would be 1 over 2,500ths of a second per revolution. No, that's not right. 60 over, that's probably why I did it, to not be confused. Okay, so I'm going to do it. I'm going to leave, I'll tell you what I did. You know what? I've done these for years. I must be doing something right. I'm going to do 1 minute, okay, just to keep it simple. So if I do it for 1 minute, the benefit of doing that is I'm going to be doing exactly 2,500 revolutions. So I'm going to do 2,500 times the difference in each cycle, and then divide that by 60. It's not a big difference. It's the same answer. So I'm going to do the work in each cycle from the engine. Is the difference between these has got 3.31. Is that right? No, that's 3.31. Yeah, 3.31. So the work is going to be 3.31 times 10 to the third joules in each cycle, times 2,500 cycles. This is joules per revolution. 2,500 revolutions per minute times 1 minute. Okay. And then divide that by 60 seconds. Did I get that? Okay. You could have done it slightly differently, but 1 revolution. Okay, so what do you get? A big number. We're going to get a power of about 138,000. What are the units of power, by the way? Those are watts. Another W. Woo! But at the end of the number. Okay. Sometimes earlier in physics you get confused by all that. W, W, W. What's what? So another way to state that would be 138 kilowatts. Okay. They asked you for the power not in kilowatts, though. Even though that's the preferred unit for physics, they asked you for the power in horsepower. Find the power in horsepower. I don't know that. Do you guys know the number, the conversion offhand? I don't either. So I went and looked it up. It's in the back of the book. The conversion is 1 horsepower is 0.746 kilowatts. So 1 horsepower is 746, right? 746 kilowatts. So it works out pretty nicely here. We get 185 horsepower. Okay, 185 horsepower. Okay, 2 down. How about letter C? Okay, now here's where we're going to talk a little bit about this omega. The correct units for omega should be radians per second. And you want to know that you need that for this third part. They ask you for the torque being output to the cylinder shaft. Okay, so what is torque? Anybody have a memory about torque? How is torque going to relate to stuff that we've learned about already? Okay, so the torque is going to be related to the power, right? Torque is power. Torque is going to relate to the work being done by the engine. Actually, so when I say work being done by an engine, the shaft is rotating. Torque is what's causing that rotation to occur. Can anybody come up? What's the form? Do you guys already have a formula for how torque fits into work? Or torque fits into power? No? Okay, so actually this is an important point because I think you better figure this one out. Okay, so what is torque? How is torque going to be related? I'm going to actually write this down for you. Work is force times distance. Okay, I know it's FD cosine theta, right? Okay. But we're going to assume that the 90-degree angle is happening here, right? So I can forget about that term. That familiar? Force times distance. Okay, that's an easy formula. If you're rotating an object by applying a force to the edge of it, right, like what this thing is doing, then another way to do this is to say force times r times theta, where theta is measured in radians. Does that make sense? Okay, r times theta is an arc length. Well, what's force times r? If I'm doing it right, that's my torque. Okay, so there you go. That's the relationship that we were trying to figure out. So work is going to be the torque times the angle through which that torque causes the object to rotate. There we've got work. So now what's power? Work divided by time. So I'm going to throw this in. Torque times theta over t. And you look at this theta over t and you say what? That's going to be omega. So torque times omega is in fact the power. And I found the power. So in order to find the torque, what do I need to do? That's it. The torque is simply the power divided by the angular velocity. It is important that you get the units right, though, or this isn't going to work. So theta is measured in radians. My omega needs to be in radians per second. All right, so we'd have to do a little conversion. So our 2,500 revolutions per minute. One revolution has how many radians? 2 pi. Okay, so I got 2 pi radians in one revolution. I've got, in 1 minute, I've got 60 seconds. Okay, so you got to do that off to the side there. And I've done that for you. I get 262 radians per second. Okay, so now it's pretty simple. We can apply. Actually, I'm going to use the watts again, right? Because that's what goes together with my calculation for energy. So I'm going to use my 138,000 watts divided by 262 radians per second. And lo and behold, we get 527 Newton meters. It all just works, you know. So you can go through there and figure it out if you like. Yes? Oh, you know, I knew someone was going to ask me. I can do that conversion. I just don't care to. So how do you convert it, right? What's the deal? If you have 1 pound of force, that's equivalent to a mass. Sorry, I did it backwards. 1 kilogram of mass has a weight of 2.2 pounds. So then 1 kilogram has a weight of 10 newtons, or 9.8 newtons, sorry, 9.8 newtons. 9.8 newtons is the conversion factor to 2.2 pounds. 1 foot is 0.3048 meter. You want me to convert this, really? Oh, man. Okay. All right, thank you. So, all right, so you need 2 conversion factors. You got to convert the newtons into pounds and the meters into feet. Okay, you need 2 conversion factors. I think I just told you one, right? So I said that 2.2 pounds equals 9.8 newtons. Okay, that's my conversion for newtons. And then, do you need this? You guys need this? Raise your hand if you're a student, you need this. Okay, but you're going to go out and work in the real world, and a lot of engineers still use foot pounds. Okay, so we're going to do it anyways. Okay, and then we have 1 meter, 0.3048 feet. That's what I remember. Okay, so conversion. I didn't do this. This is all ad lib, by the way. So you guys on the fly here. 2.2 pounds. Convert that. Let's see, I got to get rid of my meters. So 1 meter, 0.3048 feet. Okay, so multiply that by 0.66, it looks like, is the right way to convert between, and I don't have a calculator, so I'm going to rely on somebody to do that for me. Multiply by 2.2, multiply by 0.3048, and you get... oh, sorry, and divide by 9.8. Okay, I messed up. So 0.066, huh?
36.1.
36.1. Okay, cool. 36.1 foot pounds. Okay, that's actually how mechanic might do an actual torque, foot pound. Okay, 1 down. We only have 5 more to go. Do you think we can get these done? I'm supposed to have 20 minutes per, but there are some easy ones. That one wasn't too hard, but it has a lot of calculational type of stuff. Oh, I'm not done. Oops, that was C. Right, I did C. That was C. Finding the torque was C. And there's one more problem, okay? The last problem says D. What power must the exhaust and cooling system transfer out of the engine? So which heat energy is being exhausted out of the engine? That's QC right there. So in order to find the power that my cooling system has to be able to dissipate, I'm going to use QC as my work or my energy divided by the time. So that's a pretty straightforward calculation. Again, I did for 1 minute just for the sake of, all right, where am I working? I'm going to work all the way over here at the end. D. I'm going to pick up my paper so I don't have to go back to it. Okay, so the last problem, D. The power of the cooling system. Okay, so the power is still going to be energy divided by time. We're taking the cool heat away from the engine in a time t. I'm going to use a t of 1 minute, 60 seconds. And so what's the heat energy? In one cycle, we have 4.58 times 10 to the third joules per rev. I have my 2,500 revolutions per minute times 1 minute. Okay, gives me a lot of energy. 1.145 times 10 to the 7th joules to divide that by 60 seconds. Okay, and you end up with a power of 191,000 watts or 191 kilowatts. Okay, my cooling system has to be able to dissipate energy at this rate in order to function properly. It should be greater than that, right? You don't want to have it just right at that maximum. You need to be able to get rid of all of the heat energy, nothing left. Okay, we got an easy problem though. So thankfully we have an easy problem. And it is not any pictures either. So problem number 14. One down. 5 to go. I don't know, I hope there's some more easy ones though. Okay, number 14.
Very ambitious.
What's that?
He's very ambitious.
Yeah. Number 14, here we go. We got a power plant operates at 32.0 efficiency during the summer when the seawater used for cooling is at 20 degrees Celsius. The plant uses 350 degrees Celsius steam to drive turbines. If the plant's efficiency changes in the same proportion as the ideal efficiency, what are they referring to there? The Carnot cycle, okay. In the same proportion, what is the plant's efficiency in the winter when the seawater is 10 degrees Celsius? So the seawater cools off in the winter, it's warmer in the summer. The efficiency changes because of that difference in temperature. So we'll start off. Should we start off with the Carnot efficiency first? Let's start off with that, because that's a nice, that's an easy problem. So we're doing number 14 here. Okay, I don't think this one will take more than a board. This is a nice, quick little problem. Okay, number 14. So they tell us that the steam is 350 degrees Celsius. So I'm going to write that down, that the steam has a hot temperature, right, of 350 degrees Celsius. But in the summer, my cooling seawater is 20 degrees Celsius, and in the winter, the cooling water is 10 degrees Celsius. That's my difference between them. So T cold is going to have two values. So T cold in the summer is going to be 20 degrees, okay? And T cold in the winter is going to be 10, okay? So what's the formula for efficiency when you're talking about the Carnot cycle?
Delta T over T hot.
Okay, cool. All right, delta T over T hot.
Or you can say 1 minus.
Now, delta T over T hot. Okay, delta T over T hot. I always learned 1 minus T cold over T hot, but I like that one, actually. I think it's good to know both. Okay, so you got T hot minus T cold over T hot. Oops, T hot. Or the one that I always remember is just 1 minus T cold over T hot. Okay, so what do we got? We got difference between 350 and 20, right? Okay, number one mistake. No, stop. What's wrong with degrees Celsius? It's the wrong temperature scale. Wrong, stop. Okay, don't do degrees C. It's a common mistake. But this one's not going to work. It's just the wrong scale. It screws you up everywhere when you're doing thermodynamics and gases. You know, it's just the wrong thing. So what's the right scale? Kelvin. All right, so let's go to Kelvin, our true friend in this problem. The temperature of 350 works out to be 623 Kelvin. There we go. That's right. Okay, that's the correct way to think about it. If you think about it, because if you were at 0 degrees Celsius, are you at 0 energy? Not even close. You're actually at 273 Kelvin. That's a huge amount of energy. 293 Kelvin. 283 Kelvin. Okay, there we go. So the Carnot cycle is also going to have a difference in its efficiency. And the one that they tell us in the problem is the summertime efficiency. The one we want to find is the wintertime efficiency. I generally like to put the thing that I'm trying to find on top when I have a ratio. Are you guys good with that? That's the way I do it. So what I want to get is I want to get the ratio of the Carnot efficiencies, summer to winter or winter to summer. But because the one I want to find is winter, I'm going to put that on the top. I want the Carnot efficiency in the winter divided by the Carnot efficiency in the summer. I want that ratio. Because my factory, my plant, whatever this is, I read this. My operating plant, my power plant, that's what it is. Okay, my power plant is going to have the same ratio. So it's going to be equal to the efficiency of the power plant in the winter divided by the efficiency of the power plant in the summer. They're giving me this information. And by the way, this is a good first guess about how the system might work. It probably won't be that good, but it's a good first guess. So they told me this one is 32%. So the one that I'm looking for, the efficiency in the winter, is going to be somehow related to that 32% that they give me in the problem. Okay, you'll notice that I wrote the efficiency as a fraction. That's the right way to talk about the efficiency, right? You write it as a decimal number. Okay, so let's go to work. How do you find the Carnot efficiency? You do delta T over T hot. That's cool. And then the delta T, in fact, is 330. Okay, that's great. Over T hot. Okay, so we got my ECW. We'll do that first. It's going to be, let's see, winter time. Summertime, T hot. Okay, so what's the difference? 340 over 623. That's my wintertime efficiency. Or 1 minus 283 over 623. And that efficiency works out to be 0.5457. Keep one extra number in the middle of my calculation. And in the summertime, the Carnot efficiency is going to be a little bit better or worse? Worse. Because the temperature difference is not as large. We want this difference to be as large as possible to have the highest efficiency. If you could theoretically make the cold temperature 0, what would the efficiency be? It'd be 100% efficient. Man, if we could just do that, get it to absolute 0, we'd have the miracle machine. Yeah, okay. Not possible, right? Anyways, okay, here we go. So the difference is going to be 330 Kelvin over 623. Not going to be quite as good. 0.5297. Hey, 0.5297, 52.97% efficient. So now I'm ready to set this up. I've got my two numbers for the Carnot efficiency. I'm going to put them in here. And I want to solve for the winter efficiency of the factory. So what I'm going to do is multiply both sides by 0.32. Okay, everybody good with that? Easy? Okay. So the efficiency in the winter for my factory should be the ratio of these two Carnot efficiency, 0.5457, 0.5297, slightly over 1, right? Just a little bit over 1, times 0.320. So it should be just a little more efficient. And in fact, I get 0.330, or 33% efficiency. Big jump in efficiency. You got a whole percent, which is something significant, actually, right? So it gets 1% more efficient in the winter than it is in the summertime, just from that difference in the seawater temperature. Woo! 2 down. Yeah. All right, 2 down. And now we have a juicy one. This is juicy. This one takes like 3 sheets of paper. I'm not kidding. And by the way, I just did these last night. This is my homework, right? I should have done them before, I know. But hey, I got them done. Okay. And this one takes a few sheets of paper. So you want to listen to this one. And we have a graphic for this one. This is problem number 20. Maybe we don't. Problem 20.
They're not necessarily in order, by the way.
Oh, they're not in order. Okay, that's very helpful to know. I'm looking for an, oh, you know what? It just describes it. So maybe there's no picture. So it's a Carnot cycle, though. Anybody see a Carnot cycle? I don't even see a Carnot cycle.
There is one.
There is one, right? This is not. Is this one?
Yeah.
Yeah, that's a Carnot cycle. Okay, cool. That's good enough. We'll just look at that then. So just to remind you guys know Carnot cycles pretty well, right? Okay. Starting at the top, A. You're writing down the isotherm. And number one idea, right? If you're writing down the isotherm, then your volume is increasing. It's an isothermal expansion of the gas, right? You just look at it. That's what it's doing. It's going to a bigger volume, but it's isothermal expansion. And then the little bit stranger, but also beautiful, jump from one isotherm to another. You're going along an adiabatic curve, right? And remind me again, what does adiabatic mean? No transfer of heat. The walls don't allow the penetration of the heat. Now, how does that happen in reality? What do you do to make a system adiabatic? You've got insulated walls, or do it very, very quickly. Okay, very, very quickly. Okay, and then we have this other part right here where you're going backwards, right? Again, along another isotherm. So the jump between isotherms is what the adiabatic is doing, right? We're jumping from one isotherm to another. And when we do that, we're changing the internal energy of the system, right? So, all right. Yeah, everybody knows isotherm. You guys have done this for a while. Okay, so this is going to be isothermal compression. And this is adiabatic expansion, sorry. Isothermal compression and adiabatic compression for the final part of the cycle. Okay, so we've got the things that they are, and then we need some relationships. Okay, so this is going to be a fun problem. This is problem number 20. And let me read it, and then I'll write down again the relevant information. It's a big, long problem. I'm going to have to erase everything a couple of times. I'm not kidding. It's going to take a little while. But there's going to be two sets of data that we're going to collect. So we have to first kind of solve a little puzzle about the cycle. They give us some of the pressures and volumes and temperatures, and we've got to find all the rest. So they give us something, they give us enough information that we can figure it out. But you guys have to find a way to link the points that you do know with all these other points that you don't know. So it's a fun little puzzle. That's the fun part. Actually, that's pretty fun. And then we have to worry about the cycles themselves. So we worry about the amount of heat energy. And as the diagram is showing, where does the heat energy flow into the system? Along the isothermal expansion, right? As it expands, it's doing work, but the energy is not changing. So it has to take in heat energy to compensate for the work that is being done by the gas as it expands, right? So the net change in energy is zero. No change in energy on an isotherm. Let me read the problem. At point A, here we go, in a Carnot cycle, 2.34 moles of a monatomic ideal gas has a pressure of 1,400 kilopascals, a volume of 10 liters, and a temperature of 720 K. The gas expands isothermally to point B, which they don't tell you anything about, okay? And then expands adiabatically to point C, where its volume is 24 liters. And isothermal compression brings it to point D, where its volume is 15 liters. An adiabatic process returns the gas to point A. Determine all the unknown pressures, volumes, and temperatures as you fill in the following table. Okay?
I was just wondering if you want to view the questions here.
You have it like a,
The PDF.
you've got a PDF?
Yeah.
That'd be awesome. How do I get to it? Can you get to it for me? You're awesome. Look at this. He's going to make it so much easier for us. Thank you for that. That's great. Just go open a browser or something. Okay. Do you need to?
No, I got it.
Okay, you got it. I got this. I got this. Good. I love that. That's great. If you could just say, I got it, let's take off. Okay, so we're doing a long problem, but we're going to keep two tables right here of information. One of them, all of the pressures, the volumes, and temperatures. And then a little bit later, okay. Ooh, okay. All right.
Can we read the internship essay?
What's that? All right, don't look at his password. Okay. And also for the second part, we're going to calculate the work and the heat energy that's going in and out of the system so that we can calculate the total work being done by the system and the efficiency and so forth. Okay? So let's go ahead and make a little table right now. And these are the two tables that we're going to be filling in just a moment. Okay, so we have, actually I've got the solution here. Okay, so we have our state. We have our state. We have our pressure in kilopascals. We have our volume in liters, although every single time I use the liters, I'm going to be changing it probably. Oh, look at this. This is great. Awesome. Is that on the system now?
Yeah.
Oh, thank you. That's cool. Great. Oh, what a relief. Yeah. And then we have the temperature in Kelvin. Okay, so we have our state A. They tell us the pressure is 1400. The volume is 10. The temperature is 720. Okay, now you can all read that. Oh, there you go. I'm just copying that table. You can copy that table as well. B, we don't know anything really. C, or do we know anything at B? Sorry, just before I go on. Do we know anything about B at all? Is it on the same isotherm as A? Yeah. What does isotherm mean? We know the temperature. Thankfully, we know something. Okay, good. We know something. We know that the temperature is the same. Okay, isotherm. Part C, they tell us that the volume is 24. And D, we are given that the volume is 15. Okay? So we got a lot of work, we've got a lot of things left to figure out. This is a fun problem though. This is more like, I don't know if anybody good at Sudoku, right? This is a Sudoku right here. You got to fill in the numbers that are missing. You know, use the clues, figure it out. It's not that bad. Now we're going to have another table right after that, which is also going to have A, B, C. Actually, why don't I just tack it on? Can I just tack it on? Let's write it right here. What are the relevant things that we would want to talk about in our system? We'd want to talk about the amount of heat energy, and probably kilojoules would be good. The amount of heat energy flowing in or out of the system. We want to talk about the work being done. Now, actually, this is the part that's important. In the book, they stress the work done on the gas. This is a little strange for me. I'm fine, I'll do that, that's cool. But what I'm used to doing is the work done by the gas. Okay, so it's really important that you keep that straight. But it's very simple to keep straight. If a gas is expanding, it's pushing its environment out, it is doing positive work. The gas must be losing energy as a result of doing that. It's simple, that's it. The energy must be going down, right? Or losing that much work energy. If it's being compressed, it's doing negative work. Somebody else is pushing in on it. It must be gaining the energy from that. So your delta U, when you talk about the change in internal energy of the system, they write Q plus W. That work must be the work being done on the gas in that case, okay? All right, so let's see. Well, actually, what's the work measured in? Let's do kilojoules again. And what's my last column? Anybody know? Delta U, good job, all right. The work in kilojoules, and then the delta U. Okay, so you got A, B, C, D.
Those aren't aren't at A, B, C, D. Those are from A to B and then from B.
Those aren't what?
Those aren't at A, B, C, and D. Those are from A to B and then B to
No. Oh, yes, you're right. Oh, that's a good point. That's a good point. Yeah, no, you're right. No, I messed up. Okay, he's right. Okay, so just put them over here? Yes, okay. A to B. Well, yeah, we need 4 of them. I got 4 rows. Okay, that's cool. B to C. Thank you for that. That's definitely a big mistake. D to A. Okay. That's a good one. Okay, great. Good. Ooh, that would be a little confusing. Yeah. No work is being done at a point. Oops. Okay. All right, great. So let's do our little puzzle, right? Our little puzzle problem. How do we do that? We start off with what we know. Okay, so we start off with what we know, and we try to find something that we don't know. Okay, so what are our 2 big tools that we're going to want to use in order to do that? The number 1 equation, PV equals nRT. There we go. We know that that is true. We know that they give us further, the number of moles is 2.34. 2.34 moles. Everybody know R, the value for R? 8.31. Okay, I like that number. 8.31 joules per mole Kelvin, okay? The problem is they did liters. Every little calculation that I do, I'm going to change it into what? Cubic meters, okay? Cubic meters. And then kPa, I'm going to have to think about that number is truly in Pascal, right? So when I do my calculations, I'm going to use Pascals. Okay, so what's the clue? What are the 2? This is one of them. And then another one. So what happens during, there's basically 2 things. We've got isothermal. And what's important there? The T is constant. Okay, so which equation can I use? I could use this. It's great. Right? Isothermal process. This whole side is constant. And that means that I could start off by saying things like PA VA equals PB VB. That's great. Except there's 2 unknowns there. So I'm going to have trouble solving that. I actually don't think I can do that right now. Okay? You guys see that? There's 2 things that I don't know. I don't know either the pressure or the volume. I can't actually figure it out. Okay? So we're going to come back to that, right? That's the idea. If you can't do it, well, there's probably something else that we could do. And you want to remember that because it's a cycle, A goes to B, and B goes to C, and C goes to D, but then D goes back to A. So A and D are connected as well. Does that make sense? As a cycle. But not by an isotherm. What's the connection between them? That's an adiabatic. For an adiabatic process, there was another relationship that you would want to talk about. What happens during an adiabatic process? P times V to the gamma is equal to a constant. Okay? And I think you derived that at some point. They mentioned monatomic ideal gas, which you love because that's the simplest thing you can have. And if you remember, you could go look it up if you don't remember. But it has to do with the degrees of freedom, right? Monatomic ideal gas only has translational kinetic energy, right? That's simple. And so it becomes a very simple value for monatomic ideal gas. You're going to end up with 1.67, 1.66. I think they put 1.66 in your book. I probably would round it off to 1.67 personally, but hey, that's all right. We'll use your book. So if you think about it, A and D are the other things. Since I have so much information with A, I might be able to connect it to D. Let's try going that way, all right? So that means that one side, PA, VA to the gamma equals PD, VD to the gamma. That must be true. And if you look, because I've got one of those things, I should be able to find the other one. Okay? So that's basically my approach. I'm looking for a way to connect things. They're either isothermal or adiabatic. And A is connected to D. I'm going to try that way first. So solving for, what am I solving for? PD. I just want to get that. PD. So PD is going to be, just bring this over here, PA times, let's see, VA to the gamma over VD to the gamma. If you're like me, you want to try to be a little lazy, and do the calculation for gamma just one time, raise it to the gamma power one time, you could write it as PA times VA over VD to the gamma power. Okay, that's probably what I would do. So you've got VA, 10, over VD, 15, 10 over 15, less than 1, right? It's going to be 2/3, right? 2/3 to the 1.66 power. The point is, what's going to be true about that factor? Greater than 1 or less than 1? This is 2/3. So when you raise it to a power, you get an even smaller number, right? So this is going to be less pressure. Does that make sense? Does it make sense that it's less pressure? Yes, because to get from D to A, we had to go up to a higher pressure to go from D to A. So D must be a lower pressure. Let's see what we get. So we've got the pressure at point D, and the calculation gives, I got 711, but the answer says 712 kPa, right? So I put in that 712. Now, I'm actually going to stop for a second and point something out to you, that the only number missing for point D is the letter T. And we have this formula right here. And we know the pressure, the volume, the number of moles, and the constant, ideal gas constant. We can find T, right? We can find it. So in fact, to fill in this number, which is going to be my second isotherm, I'm going to go back to the ideal gas equation. And I'm going to write down that T must be P times V over N times R. But I need my units to be right, okay? Otherwise it won't work out. So let's go ahead and tell me what would the pressure have to be? So 712,000 pascals is the correct. So I'm going to use the pressure at D, the volume at D, and the number of moles is constant, and R is a constant. I can find the temperature at D. The pressure is here. What's the volume? 15 liters. Yeah, divide by 1,000. 0.015 cubic meters. Another little common mistake. If you don't do that, the value of R is not correct, right? That value of R doesn't fit with liters. It's actually not the right number at all. You could figure out what that number should be by going back to A, and you could have a new value of R, but why bother? Let's just convert it to something easy. Divided by 2.34 times 8.31 joules per mole Kelvin. Okay? And using that, we end up finding out that the temperature is 549 Kelvin. Okay, so 549. But C and D are linked by another isotherm. So I'm back to saying that this is 549 as well. Cool. And now play the same game, except C is missing the pressure. So what we're going to do is apply this to find the pressure for C. So the pressure for C, solving that, the pressure for C must be N, R, the temperature of C, divided by the volume at C. There it is. So we're almost done, right? We're practically there. You can feel it. There's only one thing left, B, that B where they didn't give us anything, right? How do we get to that? Right, so we're going to go N, 2.34, 8.31, 549 divided by 0.024, right? 0.024. And we end up with, for C, I end up with 445 kilopascals. All right, and the last one, linking B and C together by what? By an adiabatic process. So that's going to be our final thing, and then we will, well, almost. We got two more things, right? We got to figure out the final, what are we going to get from this? See, what are we going to get? Oh, I see. Wait a second. I think we have to do both, don't we? I forgot. What did I do? Yeah, we have two unknowns, right? So we have two unknowns. I don't know how we're going to do that. Huh? How are we going to do that? We need two equations, right? Let's see what I got here. Okay. You see how to do it? I hope you're sensing it right here. So the pressure at C times the volume at C to the gamma must be equal to the pressure at B times the volume at B to the gamma, right? They're linked by an adiabatic process. Okay, so what do I not know? Well, I don't know the pressure at B and the volume at B. That's no good. I can't actually solve this either. So, anybody have an idea? I have two unknowns. Oh, what? Oh, darn it. That's what I can do, right? Come back to my first equation. The pressure at A times the volume at A equals the pressure at B times the volume at B. That's the clue, okay? So we have a way to describe how pressure and volume are related. That's great. So how is pressure, let's see, I'm going to do, what should I do? What's the easy one? Is it easier to solve for pressure and plug it in here, or solve for V and plug it in here?
Why don't you just divide through?
It's not a big deal, is it? Yeah. Okay, what do you want to do?
Divide through.
Okay, so divide by P? Okay. Or divide by P or divide by B?
The two equations by each other.
Oh!
That way you just have V.
Awesome. Okay, let's do that. I like that. That's a good trick. Yeah, I was going to substitute the same thing, but that's cool. I like it. Let's do that. Okay? So we're dividing this side, and the PBs are going to cancel each other. That's pretty cool, right? And we end up with VB to the gamma minus 1. Right? Now, what's gamma? 1.66 minus 1. So you end up with 0.66, right? 0.66. And it equals, so it's going to be to the 2/3 power, just for the sake of simplicity, right? And then over here I'm going to have PC over PA, VC to the gamma, VA to the VA. Okay, I guess I got to put it all in. Okay, PC, VC to the 5/3 over PA, VA. Okay, mine was not easier than this. Huh, okay. I did get one solution. So what's the final, see, I think my way was a little easier, but that's okay. Let's do it. That's okay, fine. The reason I was looking for that, what did I do? Let's see, I solved for, because I only had to do one exponent. Well, whatever. It's what it is. Okay, actually I got the same thing. Never mind, I got the same thing. I know what I did. Okay, so how do you get rid of the exponent here? You're going to raise it to the 3/2 power. Going to raise it to the 3/2 power, right? Well, that's the hardest part maybe. So to find VB, here we go. We got a bunch of numbers. So this is a little bit of a calculation though, right? But we have PC and PA. Those don't have to be converted because the units are going to cancel. But the volume must be converted into cubic meters, okay, before you do this calculation. I mean, I could throw all those numbers in there. You can look them up on the table right there. You should get a final volume for B. You should get 16 liters. Okay, this becomes 16 liters. Okay, so from this solution right here, if you plug in PC, I mean, it's 445 over 0.024 to the 5/3, and then PA 1400 over 0.01. Okay, raise that to the 3/2 power. It's a little just mess, right? But you should get 16 liters out of that. Okay, finally, last step. How do we get this B? We go back to the ideal gas law. Okay, finally, as the ideal gas law, the pressure at B is going to be NR, the temperature at B divided by the volume at B. And we're finally done. We've filled in the whole entire table. Wow, aren't we awesome? 875 kilopascals. Okay, so that was hard, but actually kind of cool, right? You see the linkage between the different steps of the cycle. But now we need to do a little bit of work, literally, right? We need to find the work, we need to find the Q, we need to find the change in energy. So let's do the easy ones first, okay? What are the easy things to think about for a Carnot cycle? When you're on an isotherm, what's happening to your energy? It's not changing, right? The energy is not changing. So I'm going to put this in right away. From A to B, there's no change in internal energy. And then the other isotherm was from C to D. There's no change in internal energy. I'm going to put those in because those are easy, right? They're give me. As soon as you have an isotherm, you know the energy is constant. But I'm going to need a couple of tools right now. So he told me to not let you rely on equation sheets because you don't get an equation sheet, right? You have to memorize all of this.
No, derive.
What do you get?
Derive.
You have to derive. No problem, derive it. So, do you remember that time in September when we were young? No, you don't. Do you know that one? Yeah. Good job. Okay, do you remember how to derive the work being done during an isothermal process? Is that pretty easy? I mean, that should be pretty easy. There's what I'm going to start with, right? For an isothermal process, I can, what's my formula for work? My work is negative, right? The work being done on the gas. It's the work being done is PdV, right? The volume has to change in order for work to be done. This is a really big deal. If the volume's not changing, how much work is being done? Nothing. So you don't have to worry about the VDP term, right? That's just not that's not relevant to our thing. Did anybody get that point? That's okay, don't worry about it. All right, so here we go, PdV. So we want to solve for pressure as a function of volume. And that's just simple, right? Pressure is nRT divided by V. Hey, do I need to do this, or do you guys just totally remember it?
Got it.
Got it, okay. So what do we get? Our work is going to be negative the natural log, negative nRT natural log of V final over V initial. Okay, that's what you have as your formula. Okay, I mean, I won't derive it if you don't need me to. There is one, the adiabatic. I assume you did that one too. Yes? No? Maybe? Are you really comfortable with the work being done in an adiabatic process?
It was on the homework.
You want to see it again? What's that? It was on your homework?
Yeah.
Okay, so you've done it plenty of times. And so, is it a complicated formula, the work being done?
If you don't know that,
No? Good for you. That's good. But a lot of times, I looked in your book and it's like a big long formula. I'm like, why do you write it like that? Really? Why would you do that? Just to make people confused? What? So I'm hoping you guys remember that during an adiabatic process, it's a formula that you can write down, but it can also be simplified in a very beautiful way. And I assume he did that with you, right? You end up seeing it's just the change in the internal energy. Okay, good, great. So, well, let me write it down anyways, because I need to write it down. In your book, you got a formula like this. This is isothermal. And the other one, adiabatic, is a little more energy here. We got 1 over gamma minus 1 times, I didn't write it down. Oh, shoot. Okay, V, oh yeah, I did. Here we go. V final to the 1 minus gamma minus V initial to the 1 minus gamma. Okay, but why would you want to use that formula? It's really stupid. Okay, sorry. It's just not that great. So in fact, remembering that P V gamma equals a constant, if you write V gamma is equal to that constant divided by P, well, actually, yeah, there we go, P. You can actually get something interesting. Oh, no, sorry, V to the minus gamma. V to the minus gamma, that's what I need. V to the minus gamma is P divided by that constant. Okay, so then V to the 1 minus gamma is actually P times V divided by that constant. Okay, so that's kind of a neat thing. So if you work it out, though, you end up getting a much simpler formula. You get 1 over gamma minus 1. For a monatomic ideal gas, that's going to be 1.66 minus 1.66. 1 divided by 2/3 is 3/2, right? N, R, and then it's going to be T final minus T initial. That's a much easier way to calculate the work. And just to point your attention to why this is the right formula, the internal energy of a gas is dependent only on the temperature of the gas. And for a monatomic ideal gas, we know what it is. It's 3/2 nRT. So when we jump from one isotherm to another, the internal energy is changing. That's it, right? Exactly by this amount. So you've done this. I see some of you writing this down like you haven't seen it before. Have you all seen it before? It's all good? Okay, great. Okay, so now we can go to work. Now it's pretty simple. So we're going to start off with the isothermal process right here. Let's calculate the work. Again, let's remember this is going to be the work done on the gas system. So let's predict the correct sign. What's the correct sign? If a gas is expanding, it is doing positive work. But that means that the outside force is doing negative work. Is that good? We're predicting that the answer should become negative. So we'll do that right now. Let's see. So from A to B, let's calculate the work being done. The work being done, negative nRT, 2.34. R, 8.31 joules per mole Kelvin. Times 720 times the natural log of V final, which would be 16 liters divided by 10. Okay? So this is going to be a number greater than 1, which means the natural log will be greater than 1. It'll be positive. Right? Natural log will be positive. This quantity will be positive, but with my negative in the front, I'm going to get a negative number for this work being done on the system. That means the gas did positive work. Everybody clear on that? It's very confusing, but it's not. If the gas expands, it does positive work. You don't think about it, you just know that. Okay, the gas expands, it does positive work. So I'm going to go ahead and calculate that. Then the work being done is negative 6.58 kJ. All right, so I've got my work, negative 6.58 kJ. And then I'm going to invoke this very important idea. The delta U is the heat flowing in or out plus the work being done on the gas. And if delta U is 0, which it is in this cycle, right, isothermal, there's no change in internal energy, then if I'm doing work or work is being done on me, right, that would add energy. I do this wrong? Sorry. I did this wrong. This is losing energy, sorry. It's doing work on the environment. It's losing energy because of that work being done, but it doesn't lose energy. The amount of heat flowing into the system offsets this loss of energy here. So Q equals negative W equals positive 6.58 kJ. The heat is flowing in, right? Heat is flowing in. Let's write that in. So we got a positive 6.58 and we have a negative 6.58. Perfect. Got two numbers down. See, now it's going to go fast. It's going to go nice and easy. Okay, so now we need to do from B to C. We have an adiabatic process. And you can do it the hard way or the easy way, but the easy way is right here. All right, that's the easy way. So let's go ahead and do the easy way. The easy way, I'm going to calculate delta U first, right? That's the easy way. So from B to C, which is adiabatic, I'm going to first calculate the delta U. Because I know the two temperatures, the two different isotherms, I'm going to have my 3/2, 2.34, 8.31 times the change in the temperature. So you'll notice that the temperature is going down. What does that tell me about the internal energy? It's also going down. Okay, when you look at a picture of a Carnot cycle, the trick that you want to remember, I'm sure you remember this anyways, the isotherms look like, you know, the hyperbola shape, right? But the closer you are to the origin, the lower the temperature of the isotherm is, right? The further away you are, the higher the temperature of the isotherm. You can identify very quickly that if you're going down like this, you're moving to a lower temperature. So you've got my change in internal, it should be a negative number, and in fact, It is. It's negative 4.98 kJs. So I lost 4.98 kJs. Okay. I want to just remind you that when we do D back to A, we're going to jump from the lower isotherm to the upper isotherm. It's going to be exactly the opposite. So if you're okay, because I do want to kind of try to finish all the problems, can I just go ahead and quickly fill in the D to A one? It's just going to be the opposite, right? So from D to A, we're going to gain 4.98 kJs of energy, because we're going to be jumping from the lower isotherm to the higher isotherm. Okay, that'll help me a little bit. See if I can get done. 4 more problems. Oh, we'll see. Okay, no pressure. So what are we left with? We've got to be able to do the work, right? We've got our formula for the work being done. Oh, why is this the work? Oh, we're done with that. I forgot, adiabatic. What's adiabatic mean? Woo! Oh, I thought I had a lot to do. I don't have a lot to do. That's 0. That's easy. Sweet. This one's also 0. And if that's delta U, then what is this? This is the work. Oh, I love it. That's awesome. We're almost done. Easy. Okay, you guys got that? So in an adiabatic process, no heat energy is going in or out. The change in energy is the work being done on the system. Okay? Last step, we're going to go along the isotherm, but this time we're going to be compressing it. Okay, so let's go ahead and erase this for a sec here. Although it's almost the same, isn't it? Oh, I should have just left it. Okay, sorry. So from C to D, we are on an isotherm again. And we know how to calculate the work. The work being done is going to be negative nRT natural log of, I guess, VD over VC, right? Just writing it in. The final volume divided by the initial volume. And you're going to go negative 2.34 moles, 8.31 joules per mole Kelvin. And the temperature of the lower isotherm is 549 times the natural log. The final volume is 15 over the initial volume, 24. Hey, now this is a fraction less than 1. When I take the natural log, I should get a negative number, right? And then the negative in front makes this work done on the system positive. When you make a gas compress, it gains energy from the outside work being done. And the work being done is positive 5.02 kJs. Positive 5.02 kJs. But once again, what's delta U going to be? Delta U is 0. Okay? Delta U is 0 because it's an isotherm. So if you go back to delta U equals Q plus W equals 0, what about Q? Negative 5.02. Okay? So positive 5.02, negative 5.02. All right, we're almost done. So the final part of this question, just kind of wrap it all up. It says find the energy. We did all the energies. Calculate the efficiency, part C. That should be pretty easy. How do you calculate the efficiency of a system? Work that you get out divided by the heat energy that flowed into the system to make it function in the first place. Okay, so I can finally get rid of these extra things down here and finish off. Okay, so here we go. Our efficiency, part C. Efficiency is the work we get out, the total work that we get out, divided by the heat that we put in to the system. Okay? So when you look right here, I want you to notice something important. During the adiabatic process, we lost and then we gained back because we came back to our starting point exactly the same amount of energy. So it's not a part of the problem, right? Just forget about it. So it's really the difference in energy here that ends up being the useful work that came out of the system. Remember, this is the work done on the system. To do the work by the system, I have to take the negatives of these numbers. So you take the difference, you get 1.56 kilojoules. but it's a positive 1.56 kilojoules being done by the gas, right? 1.56 kJs. Actually, I need it to be in joules, right? If I want watts. Oh, okay, 1.56 kJ divided by the efficiency. It doesn't matter because I'm doing the efficiency and divided by 6.58 kJ. The units cancel actually, so it works out. So the energy that flowed in when I was on the high temperature isotherm is what QH is, right? The energy that flowed in. And so I have an efficiency of 0.237, okay, or 23.7% efficient. So there was an easier way to get the efficiency, right? It would have been a lot easier. If that's all I really wanted to know, I could have stopped once I got the temperatures of the isotherms. The efficiency of the Carnot cycle is supposed to be what? T hot minus T cold over T hot, or 1 minus T cold over T hot, either way. The delta T, I didn't do it this way, so let's see, 171, right? 171 divided by 720. And I haven't done this calculation, so it is...
Shouldn't it be the same?
It is 0.237, okay. If everything is right, and it is. Okay, it's good. I checked it now. All right. That was a good one. That was a tough one. That was the longest problem that we had to do. So we got through that one. Let's see if we can get the last 3 done. Maybe. We'll see. Okay. Oh, we got a nice easy one, finally. Cool. Nice easy one. Number 36. So let's see if we can see 36. Yes, thank you for that. That's awesome. 36. Much easier. Oh, my God. Then I don't have to read everything. Although you guys probably find my voice nice and soothing, right? Okay, here we go. So 36, it's on 2 pages, so I'm going to end up reading it anyway, okay? Calculate the increase in the entropy of the universe. Man, this is a big job you have. When you add 20 grams of 5 degrees Celsius cream to 200 grams, I know it's a funny problem actually, 200 grams of 60 degrees C coffee. You have changed the entropy of the universe. You did such a big deal, right? This is awesome. So what happened? Calculate the increase in the entropy of the universe. What a grand way to talk about that. And then let's see, assume the specific heats of cream and coffee are both 4.2, that's water, right? 4.2 joules per gram degree Celsius. You may use the results of problem 31. That's important because we don't want to derive 31 for ourselves. That takes a little bit of work too. Did you guys do 31? You didn't, okay. So we'll just look at the results. That's cool. It's actually a pretty nice problem in itself. You can look at it if you want, if you have time. It asks you to imagine feeding energy from the hot side to the cold side in little steps, a little bit at a time. Okay, so segment the heat energy in little tiny steps so that the temperature changes only by a small amount each time. And that's actually how we define entropy change, right? ds, delta S is dq over T. The change in heat energy, or the heat energy that's flowing, divided by the current temperature at which the heat energy is floating. But they ask us to do this. This is much easier. This is great, okay? So you've got mc natural log of Tf over Ti. We're going to use that, obviously, to do our solution. It's much easier than having to derive the whole thing. If we have time, we'll derive that equation for you. Or I'll help you with another homework problem, or I'll just try to finish. Okay, so here we go. So we're doing problem number 36, and we're using the result from 31 to write down the following formula for delta S. That is mc delta T, not exactly, right? It's mc natural log of T final over T initial. It's not that bad, but it's an important little equation for this problem, obviously. They told us to use the value C, 4.18 joules per gram degree C. Okay. Actually, a simple idea. Does anybody remember the units that we typically use for entropy? No? Okay. So it's not hard. It's actually, but it's just, if you get this unit, then you should feel happy. You did something right. That's good. But if you don't get this, then you want to go back and figure out, what did I do? I didn't get the right unit. Typically, we're going to measure the entropy in joules per Kelvin. Okay, joules per Kelvin. So if I look right here at my C, you'll notice there's no Kelvin in there. But that's not really an issue, right? Because 1 step, 1 degree Celsius, is exactly 1 Kelvin. So as a matter of fact, I can, without any trouble, just write this as 4.18 joules per gram Kelvin. Everybody identify that? It's the same thing. So the temperature change in degrees C is exactly the same as the temperature change in Kelvin. So I don't have to worry about that. All right, so what I do need to be able to do is to mix coffee and cream and determine the final temperature. Does everybody remember how to do that? Hot and cold water, what do you do? What do you do?
MC delta T.
MC delta T, okay, cool. You want to do it the hard way, cool. That's great. When you have 2 of the same substances mixing together, in fact, the C's are the same, and they no longer an issue, right? You don't have to use the C in there. So it becomes a simpler problem. Does anybody remember the answer when you mix hot and cold water together? You get the weighted average. You get the average temperature, but the weighted average, right? If you use equal amounts, you get exactly the average temperature. But because we're using unequal amounts, you're going to get what's called the weighted average. Is that familiar or not?
No.
Okay, let me just show you. Yes, no? Kind of? No. No. Oh, good. So I could teach you something. Awesome. All right, so here we go. The heat that's flowing in or out of the system is 0. Q is 0. Right? There's no heat energy going in or out of the system. The heat energy was in the coffee. Some of it is going to go into the cream. Right? That's the idea. So we're going to have some heat energy lost by the coffee and some heat energy gained by the cream. But this is negative, right? And this is positive, and they add up to 0. Presumably no heat energy is being lost by the system. So yes, we'll use MC delta T then. Let's do that. So we've got M of the hot. C is the same, so I don't have to put hot on it. Delta T for the hot, plus M of the cold, C of the cold, delta T for the cold. Okay, and then we've got to write down the information. Okay, so, yeah, that's great. Cool. I could teach you something. All right. So the idea is you got a little bit of cream, right? You got your little container, just a little tiny bit. It was about 20 grams, right? The mass of the cold is 20 grams. And it's the temperature of the cold is 5 degrees C when you start. And then the coffee, got a lot more coffee. Right? The mass of the hot is, what was it, 200? 200 grams. And the temperature of the hot, 60 degrees C. So without doing the calculation, can you predict what the final temperature will be? Will it be about, midway between? No, obviously not, right? Much closer to 60, right? The answer should be between 5 and 60, if I do this right. If I get 65, I did it wrong, okay? But it should be between 5 and 60, but probably pretty close to 60. Not 60, obviously, but something close to it. All right, so here we go. I'm going to write this down. This is 0. So we've got, actually, before I do that, let me derive the weighted average, okay? Can I do that? So this C is gone. You don't need it. And we have then the mass of the hot times the delta T. Well, that's going to be the final temperature, which we're looking for, minus the starting temperature, which we were given. That's the initial temperature of the hot side. Plus the mass of the cold times, again, the final temperature, which we're looking for, minus the starting temperature of the cold. Okay. You want to pay attention that the final temperature is lower than the starting temperature of the hot. This is negative, which leads to a negative heat energy. Heat is flowing out of the coffee. And this final temperature is hotter for the cream. This is positive. Heat is flowing into the cream part of the solution. Okay? But if you kind of multiply this whole thing out, you're going to get the mass of the hot times the final temperature minus the mass of the hot times the temperature of the hot plus the mass of the cold times the final temperature minus the mass of the cold times the temperature of the cold equals 0. Gather up the terms that we want, right? I end up getting mass of the hot plus the mass of the cold times the final temperature. Bring these negative terms over to the other side, equals mass of the hot, temperature of the hot, plus the mass of the cold, temperature of the cold. Okay, the final step, divide by the total mass of the system. Okay? So this right here, if you look at it, this is exactly what we mean by a weighted average. Right? This is a weighted average. We take the mass of the hot times its temperature. It depends how much stuff we have, right? The more we have of the hot side, the more this factor will mean in my averaging. Each gram of this substance is a part of my averaging. So if I have 200 grams, each one is at 60. That's how I'm going to be putting this together, divided by the total thing. So using this calculation, we get the final temperature is 55 degrees. Okay, is that reasonable? Pretty reasonable, right? We said it was going to be closer to 60, and it is. It's almost 60. It's a little bit under. Okay, cool. So like magic. All right, now we're ready to apply our formula. So you want to understand that this system consists of two parts, but together they are going to be, overall, the whole system is going to have a change in entropy. So actually, let's just stop for a second. Ask yourself, what's happening to the coffee in this process? You're adding cream to it. Is the water that makes up the coffee, as it cools down, is it gaining entropy or losing entropy in the process of cooling down? It's losing. It's less disordered when it's traveling slower. The higher the temperature of the system, the greater the disorder of the system, the higher the entropy will be. The coffee, by cooling down, is losing entropy. Delta S should be negative for that. But the cream part is gaining temperature, and therefore must be increasing its entropy. Overall, the change in entropy must be what?
Zero.
No? 0 or above. In a process called reversible, if the process is reversible, that means you could go forward and backwards, and there is no change in entropy. But in this process, is it possible to stir your cream in and then stir it a little bit more and have the cream and coffee separate and go back to their initial conditions? No, not going to work. So there you go. In a non-reversible process, okay, what must happen to the entropy? The overall entropy must go up. Okay? So we lost a little bit of entropy in the coffee part. We gained a little bit of entropy in the cream, but the gain must be bigger than the loss. Okay, so that's our prediction. Let's see if it works. So we've got the delta S for the coffee. I put hot or 1. I don't know. What do you guys like? Hot? I put 1. Let me just put 1. Delta S 1. This is for the coffee. Okay, for the coffee. What's the delta S? Now we've got this beautiful formula. Let's use it. Okay. Once you've got this, now did you memorize this then? Or are you going to learn how to derive it? Good question. Okay, 200 grams, 4.18 joules per gram degree C. Or actually, we changed that, right? Per Kelvin. The grams cancel, and I'm left with joules per Kelvin. I'm doing something right, okay? And then we have the natural log, which is going to have no units, right? Because there's no units left inside the natural log. That's kind of an important thing to look for. The final temperature was 55 degrees. Oh, I did it wrong. I did this wrong. Oops. What's wrong? Anybody tell me what's wrong? I screwed up. That's what I did wrong. I didn't check my answer. I would have been wrong. Oops. Good thing I checked it. So right now, guys, tell me what the correct temperatures are to put into this system. I just realized where I made my mistake. I'll check my answer key right now. Okay, what was the correct temperature? So the final temperature is 55 degrees C, but that's no good. We need Kelvin. Okay? We got to talk the average, the absolute temperature. So someone help me out. I don't know what that is. What is it?
328.
328. Okay, and the initial temperature was 60, which is going to be 333. Okay, so I did it wrong. Actually, I'm going to need your help here. The final temperature is lower, a little bit lower than the initial temperature. It's a little bit lower. And therefore, this is a less than 1. This is going to give me a negative number when I take the natural log of it. When I take the natural log of this, the delta S is going to be negative, like we said it should be. The coffee is losing some of its entropy, a little bit. What's the number? Pretty small, maybe. Sorry, I need help. I messed up. What is it?
Minus 12.7.
7?
12.7.
12.7, okay. Yeah, sorry, negative 12.7 joules per Kelvin. Okay, it lost a little tiny bit of entropy. I guess I could just look it up in the manual, huh? Number 36. Alrighty, I don't see it, but we'll see if it's right in a second. Now the cream is going to gain, so delta S2. We're going to have only 20 grams, 4.18 Kelvin. And then now the natural log, and let's work on their temperatures too. So this is a little easier. It's going to be for the cold part, right? The initial temperature, the final temperature is the same thing, 328. But the initial temperature is 278, right? 278. Okay, so we've got a final temperature 328 over 278. So you want to notice, I think this will help you if you see this, that the difference in the temperatures in this system and the difference in the temperature in this system are very, very different. This is a really big change in temperature, right? Very, very, well, comparatively. And so we should get a slightly bigger number out of this. So 32.0?
13.8.
Oh, 13.8. Oh, okay, 13.8, it makes more sense. 13.8 joules, that's a positive, right? 13.8 joules per Kelvin. So how did the entropy overall change, right? The entropy of the universe has now gone up, yes. Like we said it should. By how much? 1.1 joules per Kelvin. Now, they got 1.18. They kept one more significant figure, I guess. I think if we had, we probably would have gotten that as well. So the solution, according to what we just did, is 1.1. If you keep one more significant figure, which I kind of wish I would have now, then I could get the right answer in the book, right? The total change in entropy is going to be the sum of these changes in entropy, right? And so we end up with a net gain of 1.1 joules per Kelvin for the change in entropy. Okay?
So, entropy in the universe always grows?
Which one?
Entropy in the universe always grows? Like it never ends?
Well, the universe, in our mind, is what we talked about, the two systems that are being affected. Okay. If they're isolated from the universe hasn't put anything in. That was kind of our beginning step. But the universe consists of everything and the coffee and cream. So really, when they ask that question, it sounds so grand, we're really talking about the coffee and cream itself. They kind of distracted you a little bit with the universe. But overall, how did the system change its entropy is what we're asking. Yeah. So the entropy is now greater in the universe than it was before because of this mixing. So overall, the system is more disordered, even though part of it got a little more ordered. The part that got more disordered was much more disordered than the part that was ordered. Not much more, a little more. Okay, another one down. We got 48. I think 48 is a little bit of work. No, 48's not too bad. Oh, 48's an easy one. Yay, okay, good. 48, good. Nice, easy. So 48, and then the last one is just a little bit of work too, but I think we'll get this done. 48. Okay, here we go. A heat engine operates between two reservoirs at T2 equal to 600 Kelvin and T1 equal to 350 Kelvin. It takes in 1,000 joules of energy from the higher temperature reservoir and performs 250 joules of work. Find the entropy change of the universe. Wow, another big question, right? Yeah. This affects everybody. For this process, and B, the work that could have been done by an ideal Carnot engine operating between these two reservoirs. Show that the difference between the amounts of work done in parts A and B are very simple, right? It's going to be T1, the lower temperature isotherm, times the change in entropy of the universe. Okay, so we're trying to prove something. That's kind of an easier problem, because if you can't figure out one side, you could try the other side, and then see if that works. Okay, maybe. I don't know. Problem solving skills. Okay, so we're going to try to take this process, but we're not going to do the more complicated version of entropy change. In fact, for an isotherm, the temperature is constant, right? So when you write down ds equals dq over t, right? That's a formula that you can look up in the book. For an isothermal process, this t is constant, so you take it out of the integral. In fact, you end up with the following very simple expression. What do you get? You get delta q over t, right? That's it. So we're going to use that idea, that this is going to be, we're going to use that kind of idea. The heat is flowing in from the high temperature side, but the high temperature side is a thermal reservoir. It's not going to change its temperature. Because it's not changing its temperature, we're feeding it in at a constant rate, right? We're feeding it in every step, every little bit of heat energy is going to increase the entropy by the same fixed amount.
How do you know it doesn't change temperature? How do you know it doesn't change temperature?
You know, that's, well, because you're feeding it between two reservoirs. So, yeah, you know what, you don't know for sure, but there's no other way to solve this. If they don't tell you something about like how the other parts of the curve are working, you can assume that if it's operating between two reservoirs, they must be two isothermal processes that are feeding energy in and out of the system, at least. I don't know what the rest of it is, actually. So I'm going to just go with what I know is true, and that's what they wanted you to do. I think that you could have situations where it's not, that's not the only way that heat goes in and out of the system, but this is the correct way to do this problem. So when you look at this, because they didn't give you more details about the cycle, we're going to go with the simplest thing that we can come up with. They don't give us any more detail. So we're going to assume that the work is, so it's almost, actually, if you want, I'm going to ad-lib a little here. I'm going to tell you that, again, we have the low temperature and the high temperature isotherms. And we're adding heat energy in. We're adding heat energy in, right? We're going along step A, step B. And then we don't know what's going on, but we know that we somehow get to the other side. It could be, nice simple way would be if we do this vertical line thing. No, that's not good either, is it? Because then I have to have heat flowing out. I don't know. You know what, that's not a good solution either. I don't know. I'm going to tell you how to solve the problem. And then you know what? You're going to ask Professor Young if you can, like, to clarify a little bit, like how you would know that that's really the correct way to approach the problem. But I don't see any other information, so I'm just going to go with it. So the key thing then, they tell you that the QH is 1,000 joules. Okay, let's start with that. They further tell you that the engine does something useful. It does work. Of how much? 250 joules. So what do they leave out? What do they not tell me?
QC.
The amount of wasted heat energy, right? But that's an easy thing to figure out. How do you get the amount of heat energy that's actually wasted? You subtract, right? Whatever wasn't useful work was expelled as waste heat energy. So it's 1,000 joules minus the 250 that were used. Conservation of energy, right? We're going to expel 750 joules of heat energy. So again, let's think about our system. We're adding heat energy to a system. Does that increase or decrease the entropy of the system? You're increasing it. You're adding heat energy. We just did that problem with the coffee and the cream. You add heat energy. You're increasing the heat energy or the entropy of the system. So in the first step, right, when you're moving along the hot isotherm, right, adding heat, QH, what is the delta S going to be? Delta S1, all right, delta S hot. It's going to be the heat that you added, right? QH divided by the temperature you added it at, which they gave you. What was the first? I forgot to write those down. Temperature of the hot, 600 K. And the temperature of the cold, 350. 600 K. And the temperature of the cold, 350. Okay, so we're going to do QH divided by T hot. And it's going to be a positive. I'm doing that by hand because this is just a delta. I mean, well, it's pretty easy because it's positive delta Q. There you go. It works. Okay, you don't even have to do it by hand. But it's going to be, sorry, let's take away that positive. Because I'm adding heat energy, I'm gaining my entropy in the system. Okay? So it's going to be 1,000 joules, which are added to the system, divided by 600 K. Okay, it's going to be 1 2/3, right? 1.67. Okay, 1.67 joules per Kelvin. Okay, so you're gaining that much entropy. But on the cold side, you're losing heat, right? Losing heat. QC, the delta S2, is going to be QC divided by TC. And that's going to be a negative 750 joules, I should have said. Right? You're losing that much heat energy. The heat energy is flowing out of the system, divided by 350 Kelvin. Okay, so we get negative 2.14 joules per Kelvin. Together, right, the delta S for the universe, right, that's their big way of saying the entire system, is going to go up or go down? It went down. Wow. Okay. Delta S for the entire system. So the system lost entropy. Does that mean the universe lost? Does it say, wait a second. What is the change in entropy? I did something wrong here. Let's see. Find the entropy change of the universe. Uh-oh. How does that work? I think I did something wrong.
Divided by 600K also?
No, because it happens at the low temperature. Okay, oh, because we're talking, oh, I got it. I did it wrong. I did the entropy for the system. So the universe is outside the system. Let's do that. So if the system gained 1,000 joules, what happened to the universe? I see, that's what I did wrong. You guys see that? It must have fed the system 1,000 joules of energy. You guys understand that? Okay, this is the system. Oops, I messed up. So instead of the positive heat energy flowing into the system, we have to say somehow the universe lost 1,000 joules of heat energy in feeding it into the system. Okay? And then the other way, yeah, this is the way the heat energy was gained by the universe. Okay, all right, that makes more sense. So I messed up. Thank you. You guys just helped me fix it. Either way, because we want the universe to gain entropy, right? We know that it has to gain entropy. Okay, it does. The entropy gained by the universe, because now we're talking about, so fix that, sorry about that. The entropy gained by the universe is the difference between these. It's positive 0.477 joules per Kelvin. See, let me just check that answer. 48. They got 476. Okay, pretty close. Okay, so we're pretty confident that's right. We're talking about they asked us to compare it to a Carnot cycle. So what do you know about the Carnot cycle? You can find the efficiency, right? The Carnot cycle, EC, is the difference divided by the hot, right? The difference between 600 and 350, that's 250K over 600K. The efficiency should be 0.417. Okay, 41.7% efficient. But another way to calculate the efficiency is the amount of useful work you get out divided by the amount of heat energy you fed into the system. That's the other way to calculate the efficiency. They're equivalent, right? So how would you get the work, right? The work must be the efficiency of the system times the amount of heat energy you fed into the system in the first place. That's the amount of work that we can get out. So you should have gotten from a Carnot cycle, let's put a C right here, the work from a Carnot engine. The work from a Carnot engine would be 0.417 0.417 times 1,000 joules. That's pretty easy. We should have gotten 417 joules of useful work out. Okay, that would be the Carnot efficiency. We only got 250. This one is obviously not as good as a Carnot cycle. Carnot cycle is a superior process in terms of efficiency. So how much energy did we lose, right? What was the lost energy? We lost 417 joules minus 250 joules, right? Somehow we didn't get that useful work out that we could have if we had had a more efficient cycle. So what's the difference? 167 joules were kind of wasted somehow in the engine that I actually used. So they ask you to prove that this energy is exactly the change in entropy times the low temperature isotherm. So let's check to see if that really works. So they said, let's check, is the difference in the work, I guess I could have called it delta W, right? Delta W, the difference in the work. Is the difference in the work energy out equal to T delta S, the T of the cold or the low temperature side times the change in entropy of the universe, right? Now that we got that right, I understand now what they were talking about. Okay, good. So we're going to go the temperature 350 Kelvin times the change in entropy 0.477. It looks pretty good, right? 0.476, about half, right? It's about right, okay? And I get 167 joules, okay? Okay, that make sense? All right, great. That part, I messed that up. Okay, you guys got that? Don't make that mistake, okay? So the energy's going into the system, but where did it come from? I guess that was the key to thinking about it. Okay, and finally, our last problem. How much time do we have? 10 after? 5 after? Wait, we have 5 minutes, that's it?
10 minutes.
10 minutes, okay. All right, 10 minutes, here we go. Fast and furious, problem number 55. 55, not that bad, just a little bit of work. It's actually pretty cool, pretty nice and easy. 55, oh, it's a nice square. It's square. Squares are easy, okay? Because the sides are vertical. You guys look at that verticals, what do you say? Anybody?
No work.
No work is being done because there's no change in volume. No work, and then easy work. What's the easy work? Horizontal lines. P delta V, easy, right? P delta V, because the pressure is constant. We just take that outside of our integral, we get P times the change in the volume. So the work being done is easy. The work being done is easy. There's no work, no work. Okay, cool. And then, oh, we got a little bit of algebra, but that's it. So this one's not too bad, kind of a fun one. Let's start off, figure this out. Okay, again, we're going to relate the corners by what we can relate them with, which is the ideal gas law. They tell you, let's read the problem before we go on. A 1 mole, awesome, easy. 1 mole sample of a monatomic ideal gas. Again, easy. What's gamma going to be? 1.66, right? You can derive that if you want. Is shown in the figure starting here at the initial pressure and the initial volume. And then they bump it up to 3 times the initial pressure. Okay, volume doesn't change. Then we cruise across here at that constant pressure to twice the volume. Again, easy changes that are happening in the system. And then we drop down, and then we move across. Okay, so this is going to be nice and easy. In terms of the initial pressure, the initial volume, initial temperature, find the total energy entering the system by heat per cycle, the total energy leaving the system by heat per cycle, the efficiency of the engine operating at the cycle, explain how the efficiency compares with that of an engine operating in a Carnot cycle between the same temperature extremes. Seems like a lot, but you're going to see it works out really nice and easily. Okay, so here we go. Number 55. Okay, 55. Here we go. So what's our approach? From A to B, what can you tell me about the work being done? There's no work being done. Okay, from A to B, no work is being done. But heat energy must be going into the system. Can anybody tell me exactly why that happens? What do you see happening? Are you going from a higher temperature to a lower, from a lower to a higher, or from a higher to a lower? What are we doing with our temperature? Yeah, we're moving away from the origin. We're moving to a higher temperature isotherm. The system is gaining energy. Okay, but let's see, how can we figure that out? So we're going to use the following idea, that PI, VI, I'm going to write this down, is nRTI. Make sure you leave that somewhere because we're going to use that a number of times. That's our initial starting conditions, okay? We could find the initial temperature if we know these things. It's 1 mole, we don't even need that, N. You want to just drop it? Let's just drop it. I mean, N is in there, but it's a 1. Okay? All right. Well, let's put it back in. I feel empty without it. Okay, there we go. All right. So what about PB? PB, VB equals nRTB. But what's the same? What's the same? The volume is the same. So VA and VB are the same. But the temperatures are clearly not the same. So you're going to go, what did I do? The volumes are the same. So PA, VA equals nRTI. And then I'm going to say that what's happened to the pressure at B? Or the pressure at B is 3 times the initial pressure. Okay? Is that good? All right. So the volume at A and the volume at B are the same. This is the initial pressure. I'm going to do your trick. Can I do that? Divide the equations. That was a good idea. Divide the 2 equations. Because now I just get 3, right? This cancels, they're the same volume. You get 3 equals blank, 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 TB over TI. TB over TI. TB is 3 times the initial temperature. Okay, does that make sense? Okay? Because we have 3 times the pressure, we must have had 3 times the temperature. That would have been an easier way to do it. Man, maybe I could just look at it like that. Okay. All right, so from A to B, and the work being done is 0, but delta U is going to be what? 3/2 nR delta T, right? We wrote that down before. Because we're moving from one isotherm to another, we're going to change our energy like this. So it's going to be 3/2 1 R times the delta T, which is 3Ti minus Ti, which is going to be 3RTI. Okay, nice simple thing. Okay, so that's going to be our delta U. But delta U is Q plus W. That's gone. So in fact, we just found Q is 3RTI as well. I should probably make a table, huh? Make a table? That good? I think that's a good idea. Then we'll be able to keep everything organized. So the first step, A to B, delta U is 3RTI, and the work is 0, and this is 3RTI. Okay, like that. Okay, now I can erase. Okay, we're going to go from B to C. Okay, that's good because B to C, okay? From B to C, work is being done. Definitely work is being done. The work being done is going to be P delta V.
Minus.
All right? Because what's that?
Negative P.
Oh, negative, sorry. Okay. Thank you. The work done being on the gas. Thank you. Negative. So it's negative, and that's going to be 3Pi times 2Vi minus Vi, which is just Vi. So you end up with negative 3Pi Vi. Dang, I don't know what to do with that. Yes, I do. Right here. Pi, I erased it, equals nRTI. Right here. Sub that in. Okay? What happened? We got negative 3RTI. Okay? So we got negative 3RTI. How about the trick with PV equals nRT again, right? Let's do P VC equals nRTC. Rewrite it in terms of the initial pressures, okay? So what happened to the pressure? It's 3 times the initial pressure. It's 2 times the initial volume. And don't forget, we got PIVI equals nRTI. Divide. Okay, 3 times 2 is 6. And then this cancels. 6 equals TC over TI. TC is 6 times the initial temperature. Okay? So what's the change in the internal energy? Delta U equals nR delta T. It's going to be 1R times 6Ti minus 3Ti. Oh, negative. Yeah, that's good. Never mind. That's good. It increased. What's that? So TB, if you remember TB was 3Ti. So when
too much of 3 halves.
Oh, 3 halves. Thank you. Thank you. 3 halves. That's a big deal. Oops. Okay, so 3 halves times 3 makes 9 halves. Thank you. Yeah, that'd be off. I should just look at my notes. Yep, there we go. 3 halves nRTI, or take that away. It's got 4.5 RTI. Okay, 9 halves. But delta U is Q plus W. So Q must be delta U minus W. So you got, if we lost energy, but we ended up still gaining internal energy, we must have actually gained 7.5 RTI to make that work, right? So minus a negative gives you a positive. Okay, and then we're down to, no, we're not done. Okay, got to do C to D. Okay, what's special about C to D? Another easy step, right? C to D. C to D. What's up?
Work is 0.
Okay, work is 0. Okay, put the work in, 0 again. Okay, all the energy change is going to be a heat energy change. So all I really have to do is this PD VD equals nRTD.
Yeah, but Lester's right. It's going to be the same as A to B, just opposite in magnitude, right?
No.
Why not?
Isn't it? Because it's the volume's different. Yeah, you're on a different isotherm. Yeah, I know. That would be a mistake to assume that. So let's see for sure what it ends up being. Okay, so we're going to do this PI. So rewriting this, what was the pressure at D? The pressure at D was, I keep erasing. I'm going to just redo it because you guys probably won't see it. It's 3 times, no, it's not. What's the pressure at D? PI times 2 VI equals nRTD. Divide that by PIVI equals nRTI. Okay, we get 2 equals TD over TI. So we find out that TD is 2 times the initial temperature. So not 3 this time, that's why, okay? So what's the delta U then? It's going to be nRT final, 2TI minus 6TI. Oh, 3 halves, sorry. 3 halves nRT. Okay, we get 3 halves times negative 4 makes negative 6 RTI. So negative 6 RTI. What's the Q? Negative 6 RTI. Okay, last step. D back to A again. Okay, again, pretty easy, but you got to do the steps. From D back to A, the work, negative P delta V. So we're going to get negative PI times the final velocity, final volume, VI, minus 2VI, which is going to be PIVI, right? Which we already know is nRTI. So this is going to be RTI, positive, okay? But the change in the energy is going to be delta U. It's going to be 3 halves, nR. T final is Ti minus 2Ti. Okay, we end up getting negative 3 nRTI, or just negative 3 RTI. The negative 3 RTI. What's that?
Over 2.
Well, there's, oh, sorry, over 2. Negative 3 halves, yes. Negative 1.5, okay. Oops, sorry. Good job. And then if this is delta U, how do you get your Q? Q equals delta U minus W. It's going to be negative 5 halves RTI. Okay, so we got all the stuff we need. And in the last, you're already done. But can you guys wait a minute? Finish it off? Okay, we're almost done. The question asks, what is the question? What is the total energy entering the system? Okay, so here's the total energy. Positive, positive, negative, negative. Adding this together, you get positive 10.5. This is minus 8.5. The total Q going into the system, oh, sorry, Q entering. Here's the Q entering. QH is positive 10.5 RTI. Sorry, there you go. Here's the leaving. QC, negative, that's 2.5, 8.5 RTI. Okay. What is the work being done each cycle? We put in this, we get out this. 2 RTI is what work we're getting out of our engine. What's the efficiency? The work divided by QH, 2 RTI over 10.5 RTI. Everything cancels, right? That's the kind of cool thing about this. And you get 0.2 something. Efficiency, 0.19, right? 0.19. That's not very efficient, okay? So the point is they want you to compare and contrast. Contrast that with the Carnot cycle. And in the Carnot cycle, the efficiency is T hot, EC, T hot minus T cold divided by T hot. Okay? What was the highest temperature isotherm? It was 6 times the initial temperature. That was at the far point, C, right? So it's going to be 6 Ti minus Ti over 6 Ti again. Oops, 6 Ti. So it turns out that the Carnot efficiency is 6 minus 1, 5 over 6, which is much bigger. That would be 0.84. So what can you say about the efficiency of this engine compared to the Carnot cycle? It's a lot less. It's extremely inefficient compared to the Carnot. All right, well, thank you guys very much for your patience. Hope that helped.
Thank you.
You're welcome.
Thank you.